Welcome back. And if this is your first time, then welcome. We're going to be talking more about quantum numbers, and specifically in this video, we want to look at the magnetic quantum number, M sub L, and the information that we are going to get from M sub L is about the orientation of the orbitals. So we will have a lot of drawing in this video, but also talking about how the quantum numbers relate to each other and the values that you get. So let's take a look at, finish my words here. Let's take a look at how M sub L, the magnetic quantum number, relates to L, the angular momentum quantum number. So essentially, they are related in that M sub L depends on L. So the only possible values you can get for M sub L are, again, these are possible values. It doesn't mean it's going to equal all of these values. M sub L can equal minus L, and then you go up one by one, adding 1. So another possible value of M sub L would be minus L plus 1, minus L plus 2, minus L plus 3, depending on what L is, up through 0. And then you're in the positive realm, and we get to 1 less than L, and then up to L. And so what that means, if L has a value of, let's say, 3, then the possible values of M sub L would be minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. But we're going to start with the simplest example, and that is when the angular momentum quantum number equals 0. That's the smallest possible value of L, and it gives us the simplest result. When L 0, well, what's minus L? Minus 0 is 0. So really, if we're starting at 0, going through 0, going to plus 0, that's it. It can only be 0. So this means there's only one possible result, and that the physical realm corresponds to there being only one possible orientation. Okay. This actually makes intuitive sense, because if we think about what this means when L equals 0, we talked about this last time. This is an S orbital. Again, S-Orbital is a sphere. What does an S-Orbital look like? We have a Cartesian coordinate axis system where, I'm going to label these axes, Z, X, and let's have Y coming out towards us. And going back by. Trying to do 3 dimensions here. So this is a 3-dimensional Cartesian coordinate axis. And our S orbital is a sphere in all of this. So we can even make it look more like a sphere. Imagine the light coming from down below. Okay, this is our sphere. The probability of finding an electron somewhere in this sphere. And if we imagine changing the orientation of this sphere, let's say we turn it 90 degrees, it will still look like a sphere. Say we turn it 180 degrees, it still looks like a sphere. There is only one possible orientation for this orbital, and that matches L equals 0, giving us an S orbital, and M sub L, depending on the value of L, it can only be 0. One possibility for that value from the Schrodinger equation. But then extrapolating this into space and where the electron is, there is only one possible orbital, one possible orientation of this orbital. All right, so there is our S orbital. Let's take a look at the P orbital next. Okay, so we'll give ourselves some more space here. And a little bit more ink. Okay. All right, so let's look at when, if we're looking at P orbitals, we are looking at when now, when L equals 1, P orbitals. All right, maybe you're wondering why I have an S there, plural. Well, that has to do with the result of when we look at all the possible values that we can have for M sub L. So we just defined the possible values of M sub L can be minus L, all the way up through 0 to plus L. So that means M sub L can be minus 1, or it can be 0, or it can be minus 1. I like to write or instead of putting in commas, because it doesn't mean that M sub L is all 3 of them. It means these are the possible values. And this corresponds to orientation of the orbitals. So in a previous video, we drew what the P orbitals look like. They have a dumbbell shape, I called them. And now we're going to look at the 3 different possible orientations. And it all has to do with, again, this Cartesian coordinate axis system. So if we write out one, and let's keep the axes the same. Let's put Z up top. That's fairly conventional when you do have 3 dimensions, to put the z-axis on top. When you're just in 2 dimensions, a lot of times you put y on top. But now we're putting y here. And honestly, you can define the coordinate axis system as you want. And depending on how you define it, the Schrödinger equation can be solved with everything being self-consistent. Okay, so here we have this coordinate axis system, and let's draw one of the possible orientations for the P orbitals. Okay, some more ink. So we've got this dumbbell shape, and notice I'm drawing it along the x-axis here. We have lobes on either side along the x-axis. I didn't draw that perfectly. That's okay. So this orbital lying along the x-axis, this is defined as a px orbital. And I am going to label this as m sub l minus 1. Okay. Now, depending on what level of chemistry you're at, it is totally fine to define m sub l being minus 1 to be matching the px orbital. If you're at an upper level and you're actually solving the Schrödinger equation, then it depends on how specifically you have defined your coordinate axis system. Okay. So we know that there are 3 orientations. There's our m sub l is minus 1. Here is our m sub l equals 0. C, X. Again, here's our Y coming out. This is supposed to be coming out towards us, out of the paper. Going here, going back behind. Okay. So this m sub l equals 0. This does correspond to the PZ orbital along the Z axis. Here are lobes. Here's the probability of finding an electron. PZ. And finally, our PY. And our final value of m sub l. Plus 1. This one's a little bit harder to draw because we have our it's going to be coming out of the paper here. So I might just draw the lobe coming out towards us first, and then have our y-axis kind of coming out from this lobe. Oh, that reminds me, I didn't label my y-axis over here. Maybe we'll see that going. Same here. And then we'll use a little bit of perspective drawing and just show this lobe a little bit smaller because it's going back away from us. But it's the same idea that we have a lobe on either side. I haven't mentioned nodes yet in this video, but I will in a minute. Again, defining our axes, labeling them. Okay, so this p orbital lies along the y-axis. It follows that this is a p y orbital. Okay, now in terms of nodes, we have nodal planes here that are separating the two lobes from each other on either side. So with p orbitals, there's one nodal plane. That is a plane where there's a 0 probability of finding an electron. With our pz orbital, nodal plane is along the xy plane here. 0 probability. And in the case of the py orbital, the nodal plane is this xz plane. I can't go behind this lobe here, but it separates those two lobes from each other. All right, so here are the 3 orientations. These are the 3 that correspond to the 3 possible values of m sub L, the magnetic quantum number. Now comes the fun part. This is my favorite, actually. And this is drawing d orbitals. Get another piece of paper here. So, in this case, we now have, for d orbitals, L equals 2. All right, so for d orbitals, let's think about the possible values of m sub L. We always hearken back to the value of L. It's 2. So that means possible values of m sub L, minus 2, minus 1. All right. So what does this mean? 5 orientations. So that means we are going to draw 5 different shapes of the 5 different d orbitals. All right, so I need to somehow fit 5 onto here, so I'll have to draw a little bit smaller. And I'm going to start out with the 2 that have their lobes lying on the axes. Okay, so these 2 orbitals, I have to draw a little bit smaller. I'm going to have to squeeze everything in. Again, I'm going to have my z axis up here, the x, and my y. So this orbital is more complex. We saw that there was one nodal plane for p orbitals. Now for d orbitals, and this is not a coincidence, the number of nodal planes increases with each orbital. We had none for s, we had 1 for p, and now we have 2 for d orbitals. So that means we are going to see more lobes. And indeed, that's what we see. We can see it for this particular orbital, where each lobe, kind of like what we saw with the p orbitals, each lobe lies along z-axis. These two are kind of behind. This one looks kind of like a clover leaf. Okay, so this particular orbital, where the lobes, the four lobes lie on the axes, this is called the dx squared minus y squared. These names get more complicated, huh? Well, they need to, because we have a lot going on here, and especially if you're solving the Schrodinger equation, you're taking a lot of things into account. But for our purposes, we just want to see what is the probability of finding an electron in space, and when they're in a d orbital, well, one of the d orbitals. This is what it looks like for dx squared minus y squared. Okay, next on the docket we have the dz squared. Okay, so here we saw x squared minus y squared. The dz squared, you see z's left out here, so the dz squared is going to be lying mostly on the z-axis. So here's our one of the lobes that's on the z-axis. But then we do have some electron density around on in the x and the y plane. This ends up looking like a donut. I call this the dumbbell donut shape. I didn't make that up, but that's the common terminology that inorganic chemists use for this. Okay. So we've got most of the probability of finding an electron is in the lobes that lie along the z-axis, but this donut here is not insignificant. There's some electron density there too. And this donut lies on the xy plane. So let's not forget our axes. There's our x, there's our y. Okay, this is our dz squared, d orbital. All right, and then we have the remaining three. Because remember, there are 5, so we've taken care of 2 of them. And the other 3 look really similar to each other. They're essentially just getting rotated around on different planes. Okay, so the main difference here between the orbitals I'm about to draw and the dx squared minus y squared is for this one, the lobes lie on the axes, and for these, the lobes lie between the axes. So that means that the nodal planes are on the axes. So that means all the electron density is found between the axes. So here I'm going to draw, these lobes are all in the xz plane. So this is flat, these lobes are flat in the plane of the paper that I'm drawing. Okay, so again, these are these 3-dimensional teardrop shapes. All right. So this, let's label it XZ orbital. All right, so the other two, as I said, we're just going to rotate them. Rotate this plane of cloverleaf-shaped lobes onto a different axis. All right, so these are going to be a little bit harder to draw. So this one, I'm going to put in the YZ plane. So that's the plane that's essentially coming at chopping into the plane of the paper. So once again, the lobes are between the axes. Much harder to draw in 3 dimensions. Okay, D. So again, this is up and down, Z, Y axis. Or I'll put them in order, Y, Z. Okay, so what's remaining? We have d orbital lobes that are in the XZ axis. We have them in the YZ axis. So now we're going to draw the last d orbital that will be in the XY axis. So this will be flat. If we think horizontally flat. Get a little bit more ink. Okay. Label our axes. Okay. So now these lobes lie between the axes. Again, with this perspective drawing, it's hard to do and have it look right. This is essentially a clover leaf that's lying flat. Think of it lying flat on the ground. Okay. Flat in the XY axis. So this is our D, X, Y. There are all 5 d orbitals. Fortunately, or however you want to look at it, I don't know of anyone who ever draws f orbitals. They get very complex. We have more nodal planes, and so we don't need to worry about drawing those, or at least I'm not going to be drawing them. But I do very much enjoy drawing these d orbitals. So this is the end of this tutorial, and I really enjoy doing this. So thank you for taking this journey with me, thinking about chemistry, thinking about orbitals, and relaxing a bit.